Find the derivative of y cosine x equals x cubed, A, by implicit differentiation, B, by solving for y explicitly and differentiating the result. Show that the results are the same. So for part A, we're going to find the derivative by implicit differentiation. We have an implicit equation. We have y's and x's related to each other, but it's not solved for y in terms of x directly, and therefore it's an implicit equation. We can find the derivative by taking the derivative of both sides with respect to x, indicated by the prime. On the left side, we have a product rule of y times cosine x. So we will take the product rule, derivative of the first. Derivative of y is a 1, but because it's a y term, we get a y prime. Every time we take the derivative of a y term, we have a y prime happen. Times the second left alone, plus the first left alone, times the derivative of the second. The derivative of cosine is negative sine of x. On the right side, we have the derivative of x cubed. Its power rule, bring down the power, subtract 1 from it. So we have y prime cosine of x multiplying y times a negative sine x will be negative y sine x equals 3x squared. We want to solve for y prime here by isolating any of the y prime terms. We only have one term that has a y prime in it. It's right there. So we will add the y sine x to the other side, and we have y prime cosine x equals 3x squared plus y sine x. We can now solve for y prime by dividing by cosine of x, and we have 3x squared plus y sine x all over cosine of x. Now it is possible to make this look a little bit simpler by separating each of the terms in the numerator over that single common denominator. 3x squared over cosine of x plus y sine of x over that cosine of x. This can simplify the look of it because having a cosine of x in a denominator can turn into another trig function. The first term, we have 3x squared and then a 1 over cosine of x, which can be replaced with secant of x. And in the second term, we have y times sine x over cosine of x, which can be replaced with a tangent of x. And there's an optional way to write the resulting derivative y prime. For part B, we want to solve for y explicitly and then differentiate that result. We have y cosine of x equals x cubed. This can be solved for y by dividing both sides by cosine of x. And it will be x cubed over cosine of x. That will require a quotient rule, but we do have the option of replacing the 1 over cosine of x with a secant of x, and we can write it as x cubed times secant of x and opt for the product rule instead for the derivative. Now let's find the derivative y prime. Using the product rule, it'll be the derivative of the first. That'll be a power rule. Bring the power down, subtract 1 from it, leave the second alone, plus the first left alone times the derivative of the second. The derivative of secant of x is secant tangent each of x. So there's our y prime explicitly. We need to show that the result in part B matches the result in part A. Right now they look very similar, but not quite the same. The first term is identical, so we do not need to change that at all. The second term is where there's a little difference. We have a tangent of x in both of them, but this one has a y and this one has the x cubed secant of x. We need to see if we can make that look the same. But we have right here that y equals x cubed secant x, and that's exactly what we have right here. So that can be replaced with a y, and so we can write this as y prime equals to 3x squared secant of x plus y tangent of x, which matches exactly the results we have in part A.